welcome. In this part of the lectures, we are going to use the principles of molecular thermodynamics that we have learnt in this course so far and see the applications to different systems, and in today's lecture we are going to consider the specific heat of crystalline solids. Now, if we look at the experimental data on the molar heat capacity of metallic silver, what we find that this actually exhibits a non-monotonic increase as temperature is increased from very small values, very close to 0 Kelvin, to the higher temperatures like say 300 Kelvin. So, what we find is here initially the values are very close to 0, then there is an increase, and what happens near the top is it is attaining some constant value. Actually, this particular behavior is not specific for the kind of system for which I am showing the experimental data. Rather, this is representative of the typically what you observe as you measure the specific heat of the solid. When you are at a very high temperature, then it is found that all the solids exhibit a constant value of the heat capacity. Now, you must have studied this observation in your high school days in the form of Dulong-Pettit law. It is one of the most well known experimental observations in the studies of properties of solids. Therefore, all solids generally, when present at a very high temperature, in that case we would find that they exhibit a constant value of specific heat equal to 3 R, where R is the universal gas constant. Now, what happens if I go down to lower temperatures? When I go to very low temperature, what I find is as T goes to 0, from this constant value the CV rapidly drops down to 0, and at absolute value of 0, it is a term which is expected to be very small and nearly 0. Now, the way it approaches 0 at very low temperatures has been the subject of investigation in a very large number of studies, and in this case there was a law which has been formulated based on the generic behavior found for a very wide range of solids, and this is known as the T cubed law. So, what does the T cubed law say? The T cubed law says that as the system goes from a lower temperature to a very low temperature, then it rapidly falls down, and this fall is having a temperature dependence in the sense that in this region CV varies as T cubed as one goes from a low temperature to even lower near 0 temperatures. Therefore, it is very clear that if any microscopic modeling of this particular system like a solid, a crystalline solid is needed, it has to reproduce this kind of this set of 3 different limiting behavior of specific heat. So, but before we go into that, let us review a few more experimental cases where this T cubed law has been observed. So, what is found is this is the measurement of the heat capacity of different solids at a function of temperature at very low temperatures, and this is the measurement for potassium. And here you can see that along the x axis we are plotting T square, and here on the y axis we are plotting C by T. Therefore, it is found that C by T goes as T square for these plots for this system, which means that C at low temperatures employed here, they vary as T cubed. Similar trend is observed when you consider systems like gold or copper. So, once again at very low temperatures, if you look at the kind of low temperatures that is accessed by these kinds of experiments, you find that the T cubed law, that is C varying as T cubed, is valid. So, then the question is, all the relationships that I am showing to you applies to monatomic solids. I have done that actually to keep the treatment and understanding of the systems very simple, but this kind of behavior can also be seen for much more complicated solids as well, but for the purpose of today's lecture I am not going to cover them. So, now going back, the task is, for a given monatomic solid which is crystalline in nature, so I need to find out or calculate the specific heat of that crystalline solid, and for this purpose I am going to use the formalism of canonical ensemble. So, the prescription by now must be very clear to you. You first find out the single particle partition function for the given system, then you calculate the canonical partition function for the entire system, provided you can represent the constituent particles of the system as capital N independent non-interacting single particles. Now, obviously, once you can calculate capital Q, you can follow the prescription of molecular thermodynamics and calculate internal energy U, and then take a temperature derivative of U to find out the specific heat. So, now how do I implement this computational scheme when I am talking about a system like a silver solid or copper solid or gold solid and so on and so forth. Okay. So, for that I realize that this part is fairly standard by now. We have now tested the predictions of this prescription for many different systems that are exactly solvable within quantum mechanics. So, we know what EJs are, what Js are. So, we could calculate small q and follow this prescription to get the thermodynamic properties. But when I have a solid at hand, what I understand is, here the information that I must provide are as follows. So, what are these microstates that I represent using the index J? And if I know these microstates, what would be the associated energy value, eigenvalues of EJ? Now, in a solid, as you understand that there are constituent particles. So, if I have a monoatomic solid, in that case the constituent particles are atoms, and these atoms are strongly interacting with each other, and therefore, you cannot exactly solve the quantum mechanical equations, namely the Schrodinger equation for a system like this, which is comprised of a very large number of strongly interacting atoms. So, the next question that we ask is it possible to describe the microstates in such a way that I can still use the exactly solvable models of quantum mechanics to model the single particle canonical partition function small q. So, this is exactly what I am going to do step by step in the next few slides that I discuss here. So, let us first look at the established microscopic view of a crystalline solid. So, typically you may have studied in solid state chemistry that if you can generate a mathematical array of points which you describe in terms of lattice, you can put in the atoms for the atomic solid at these lattice points. And for example, here I have shown you some different ways in which you can create two-dimensional lattices by varying the spacing between the lattice points, the angle through which these connecting vectors are related to each other, and so on and so forth. And basically then what happens is, once you have a basic pattern defined in the unit cell, in that case what you can do is you can then go on repeating it in one direction or the other. For example, here in this case the basic unit is a hexagonal unit. This is being indefinitely repeated periodically in the x and the y direction, and that gives you a crystalline two-dimensional phase. Now, of course, most of the solid systems that we encounter are based on three-dimensional crystal structures, where the unit cells contain the atoms arranged in a specific manner in the lattice, giving rise to rather exotic three-dimensional structures such as the one of a diamond shown here, or this is a very complicated structure of a molecular solid. But as chemists, we always think about these structures as a unique structure, unique microscopic view of the crystalline solid, and this is this of course is the unique repeating unit, as you see here or here or here, that will build up the structure. But what we most of the times do not realize is that this is not the only structure possible for the microscopic state of the solid. So, what I show you here is a representative microscopic state of the solid, which would be obtained by taking one unit like this and repeating it for 3 dimensions periodically and indefinitely in the x, y and z direction. So, you will get a big cage like structure, and you would say that, well, this is a unique structure of the solid at the microscopic level. And now I am going to show you that, of course, at finite temperature, this is not going to be the unique structure of the solid, and there are many other possibilities. So, let us see why I say this. So, first of all, to keep the thing simple, I am taking a two-dimensional system where these atoms have been placed at the corners of this square, creating a regular pattern in the x y direction. Actually, I have not shown you the regular pattern in the y, I am highlighting only this portion. Okay. Now, it so happens that at finite temperature, these atoms are going to have some amount of thermal energy given by Boltzmann constant multiplied by the temperature in absolute units. Now, what will happen then? Simply because these atoms belong to a solid, they are strongly correlated to the neighboring particles that are present on the neighboring sides of the lattice. Therefore, these atoms can actually have only very limited options to use up the available thermal energy at a given temperature. So, this is how they can use it up. So, if you have a closer look at this picture, you see that this atom is more or less present at its equilibrium position at the lattice point. But look at this. This atom, which was originally present with its center at the lattice point, has moved in this direction, and this atom from its equilibrium lattice point has moved away, so that the distance between this is larger, while because of the movement of these two atoms, this distance become smaller than the lattice spacing. So, basically what we are looking at are the possible changes associated with the thermal motion of the atoms at and around the lattice points. So, it may so happen that here I have been highlighting their displacement along the x axis, but if it so happens that they are displaced along the y axis, so this is a perfect arrangement of all the atoms along the y axis, and this is where all the atoms have undergone a positive displacement to higher values of y, and this is an arrangement where each atom at the lattice point in this region is undergoing a negative displacement, in the sense that they move towards the negative direction in the y axis. And what is the net conclusion? Here we find that there is some zones of a higher density of particles compared to this, and this is a lower density region, and here very clearly we see a wave like pattern forming because of the motion of the individual atoms. Now, what are these motions? So, if we have a look at the combination of the motion of the atoms around their lattice position, either in the x direction or in the y direction, so the net result would be a collection of elastic waves with a spectrum of wavelengths, amplitudes and directions running through the crystal. So, I have several atoms strongly correlated to each other present in the system, and they are collectively undergoing displacement along the 2 degrees of freedom available to them, x and y. And simply because these are solid atoms, they can only execute a small amplitude vibrational motion about their mean equilibrium position, which is at the lattice points. Now, in the literature, these collective oscillations resulting from the displacement or the vibration of these atoms about their mean lattice positions, these collective oscillations, when quantized, are given the name phonons. Now, let us have a visual look at the different kinds of ways in which the atoms, the molecules or the particles in a lattice can use up the available thermal energy. The first one that I show here is a longitudinal wave, and as you see that in this case the entire wave front is moving in this direction. On the other hand, when I have a transverse wave, then the way the wave travels through the system is pretty different. So, now if I go back and look at what is happening to each of the particles in the medium due to whose displacement these different types of waves are coming into the picture, if you focus your attention to a particle here, you see that it is basically oscillating in the x direction. On the other hand, if I look at, and it is because of the oscillation, periodic oscillation of similar particles, I get the wave front moving in along the x direction, which is the longitudinal direction in this case. Similarly, if you look at the motion of this particle, this is this you can follow and see that how it is moving. It is remaining in this space, but how 2 different particles are moving through the medium through their displacement. Now, if you are looking at the surface of the solid, obviously the pattern of vibration, the collective vibration is going to be different. So, these are what are known as the surface waves. Okay? And if you look at a single particle on the surface, you find that this particle actually is executing a very interesting circular motion, and that is giving rise to, and when all the particles on the surface do so together, the collective motion that we see has been shown in terms of this wave, and these are known as surface waves. So, having these different types of structural fluctuations available to us, then the question is, well, what are going to be then the different microscopic states when we are considering the crystalline solid? So, one way of doing it is obviously use the ball and spring model. So, you place a ball at every point on the lattice, and then you represent the strong correlation between the position of this atom and this atom in the solid by placing a tight spring between them. So, in that case, a 2-dimensional solid can be schematically represented like this. Again, we can have the similar representation of a 3-dimensional unit cell of a solid by connecting the corners of a cube with respect to with the help of a spring. So, basically what we are seeing here is, if I want to know what these complicated vibrational patterns are, what do I have to do? I will have to say that, well, I assume that each atom is connected to its nearest neighbor via some springs which obey the Hooke's law. In that case, what I have is either in 2 dimension or in 3 dimension, I have the net vibrational pattern generated by a set of coupled simple harmonic oscillators. Now, if you think about classical mechanics or mathematical problems of solution of partial differential equations, the solutions of this kind of a problem is known regarding how to represent the coupled oscillation of a number of coupled simple harmonic oscillators in terms of an equal number of independent simple harmonic oscillators. So, this is something that is known, and I am not going to show you the solution, rather tell you qualitatively that when you solve these coupled oscillator problem for n atoms in a 3-dimensional lattice, we get 3n vibrational modes. So, basically what you say is each of these vibrational modes now behave as if they are a simple harmonic oscillator, and they are associated with some kind of a wave vector, and each wave vector of these 3n vibrational modes have a characteristic wavelength. And therefore, as you see that you can then say that this particular solid, its microscopic states can be described in terms of 3n simple harmonic oscillators which are independent of each other. That is something that is achieved by the mathematical solution of the problem of coupled harmonic oscillators, and each of these simple harmonic oscillators are characterized by a wave vector k I, that is related inversely to the wavelength of the underlying vibrational pattern, like the underlying simple harmonic oscillator representing the particular vibrational pattern. Now, here energies of these collective modes, collective vibrational modes, according to quantum mechanics at the microscopic level, these are quantized. So, these quantized energies of the vibrational modes are called phonons. So, the different microscopic states of the crystalline solid are described in the, terms of these phonons, and we understand that there is a large number of phonons present that describe the accessible microscopic states of the crystalline solid. So, at this stage we can revisit the Einstein model of solids and say that, well, here I am going to describe the vibrational motion of the atoms in terms of a collection of 3n simple harmonic oscillators at a given temperature and volume, and let us also assume that all these simple harmonic oscillators have the same angular frequency, and this frequency is given this name Einstein frequency. If that happens, then from the prescription of molecular thermodynamics, we can very easily say that for this collection of 3n simple harmonic oscillators, I can always write down what the single particle canonical partition function is, and I understand here instead of any intrinsic frequency, I am using the same frequency omega e for each of the oscillators present in the system. Now, in this way, once I know small q, following the prescription of molecular thermodynamics, I can very easily go and derive this algebraic expression for Cv. Actually, it is more customary to introduce the Einstein temperature, which is nothing but the Einstein frequency multiplied by h cross divided by the Boltzmann constant, and in terms of Einstein temperature, then the specific heat turns out to be an expression like this. So, as you see that by having a microscopic model of the solid in terms of the different collective vibrational motions, we have been able to express the specific heat as a function of temperature, because temperature appears over here, and the characteristic properties of the system in terms of its microscopic parameters appear here in terms of this Einstein temperature. So, for given values, if you can measure the values of Einstein temperature, then you should be able to find out how CV varies with respect to temperature. That is exactly what one does next. So, what I have shown here in this picture is what will be the calculated value of CV at different temperatures, and the solid lines are giving you the variations of CV calculated first at theta E equal to 1220 Kelvin and then theta E at 1300 Kelvin. And these square boxes are the initial measurement of the specific heat values of this solid, which is diamond. So, now one has this unique opportunity to look at the fact that there is clearly a discrepancy between the theoretical prediction and the observed variation in the specific heat values at very low temperature. So, the question is, how good is the Einstein model? In order to understand this, as I said, the experimental data is interpreted by looking at its limiting behavior at high temperature, low temperature, and what happens in between. So, at very high temperature, if you look at the expression for CV as predicted by the Einstein model, you will find that this quantity actually would go to 1. Whatever appears here on the right hand side, this will go to 1, okay, because I have 1 by t here. So, as t goes to infinity, this goes to 1, and if I expand, then what I have on the right hand side is 1 minus e to the power of minus theta E by t, and this I can write as 1 minus 1 plus theta E by t. So, in the expression for CV by 3R, now I have theta E by t whole square into 1 divided by theta E by t whole square, and therefore, in the limit where t is very high, this term goes to 1, which means in the limit t tending to infinity, I must be having CV tending to 3R. Now, that is a successful reproduction of the Dulong-Pettit law. Now, let us have a look at what happens when t goes to 0. When t goes to 0, I have the entire expression. If you use the L'Hopital's law, you will be able to show it very easily that CV will also go to 0. Now, here comes the most important observation that tells us that not everything is well with the Einstein model of solids. So, what I find is here, if I plot the low temperature behavior of CV in the measured data, I find that it follows the T cubed law. But if I once again look at the behavior of CV as a function of temperature for small values of t, I find that it will go as t square. Okay. So, this means that in this particular case, I do have this problem that Einstein model, although it could produce the high temperature behavior of the solid successfully, it was not able to explain the entire range of behavior of the solids, the specific heat of solids, and it failed especially in the low temperature region. So, in the next lecture, we are going to examine the shortcomings associated with the assumptions present in the Einstein model, and then review the corrections and the improvements suggested by Debye in his subsequent study of the specific heat of solids. Thank you.